Hi guys, in this video I'm going to look at the Ortur Laser Master 2 Pro, which is a laser engraving machine. It measures 600 by 570 millimeters with an engraving area of 400 by 400 millimeters. The machine is supplied as a kit, which is relatively easy to assemble. The frame is constructed from 20 by 20 millimeter aluminium extrusion and powder-coated steel plates. The carriage runs along the frame on V-wheels, driven by a NEMA 17 stepper motor, tooth belts and pulleys, with the two sides linked by a drive shaft. The laser carriage also runs on V-wheels. The stepper motor is mounted on the side of the gantry, which reduces the weight of the carriage and allows it to move faster than previous models. Limit switches are installed to prevent the machine being driven beyond its physical limits, and also for homing, which is how the machine identifies its initial starting position. The laser module that I'm testing is the LU2-4, which has a fixed focus and an optical output of 5.5 watts. There are also two other options: the LU2-4LF long focus module with an air assist nozzle, which is good for cutting, and the LU2-4SF short focus module, which is designed for engraving. The laser is focused by loosening the two screws, placing the gauge bar under the front corner of the laser housing, dropping the laser to the correct height and tightening the screws. The laser operates at a wavelength of 450 nanometers, which is in the visible light spectrum with a violet blue colour. This type of laser cannot directly engrave transparent materials, but some tricks can be employed to make it possible. The laser includes a safety shield to help prevent the laser reflecting. The control box has connectors for the power supply, USB port and offline controller. There's also a reset switch, power switch, flame alarm and an emergency stop switch. Inside the control box we have a couple of printed circuit boards. Smaller PCB is the flame detector, and on the larger PCB there's an ESP32S2 microcontroller and two HR4988SQ stepper motor drivers. The machine has a number of safety features, including an emergency stop switch, a flame detector and a shock detector. Power is supplied by a wall watt type power adapter with a 24 volt 2 amp output. Also included are printed instructions, tools, a brush, plywood samples and safety glasses. Now let's move on to the build, starting with the base frame. This is constructed from the 4-length of 2020 aluminium extrusion. First we're going to install corner brackets into the 540mm sections. The corner bracket slides into the channel, fully inserting in only one direction. T-nuts are installed into the outside channels of each 460mm section. The four sections are placed in position, with the ruler scales oriented as shown, and the frame is slid together. M5 25mm screws are used to secure the frame. And the grub screws in the corner brackets are tightened with a 2.5mm hex key. To check if the frame is square, the diagonal measurements are compared to see that they are equal. Next the belts are installed onto the tooth pulleys. And the gantry is slid onto the frame. The frame is spun around so that the back is facing forwards. Now we're going to install legs onto the two back corners. The tooth belt is inserted through a slot in the leg, and the leg is secured to the frame with an M5 8mm screw and the T-nut that we installed earlier. The end of the belt is secured with an M5 washer and an M5 8mm screw. Third leg is installed on the front right hand corner. This time the belt is lightly tensioned whilst being secured with an M5 washer and screw. Next we're going to install the Y-axis limit switch assembly. Two T-nuts are slid into the top channel of the left hand 540mm section. The belt is inserted through the slot and lightly tensioned whilst being secured with an M5 8mm screw. The control box is attached to the frame with two M5 8mm screws. Next we're going to install a drag chain bracket to the frame using an M5 8mm screw, washer and T-nut. The T-nut slots into the channel and locks when the screw is tightened. The second drag chain bracket is screwed to the gantry with two M4 6mm screws. and then the drag chain is secured to the first bracket with another two M4 6mm screws. The wiring loom connector is inserted into the socket on the control box, and at the other end the Y-axis stepper motor connector is inserted into the stepper motor socket. The other end of the drag chain can now be secured to the bracket with two M4 6mm screws. The X-axis stepper motor cables are connected together. The black X-axis limit switch wire connector is pushed onto the limit switch terminal, and the ring terminal is grounded to the carriage plate with an M5 8mm screw. I remove the paint for a good connection. The red X-axis limit switch wire connector can then be pushed onto the second limit switch terminal. At the other end of the cable loom, the Y-axis limit switch wires are pushed onto the limit switch terminals. Next, the laser module is slid onto the X-axis carriage bracket and secured with two long screws. The laser cable is plugged into the socket on the laser module, and the ring terminal grounded under a mounting screw. The cable is secured to the module with a pair of zip ties. It's then plugged into the laser connector on the other side and zip tied. Next, the focus gauge holder is installed on the front frame with M5 8mm screws and T-nuts. The cable loom is secured with zip ties. The X-axis stepper motor cable is plugged into the X-axis stepper motor, and the cable secured with a zip tie. That's the build complete. The USB cable can now be plugged in, and the power cable. And then press and hold the power button to switch the machine on. The axes should now home to the bottom left, which is the 0 position. The USB drivers should already be installed in Windows, but if they're not, they can be downloaded from the Ortur website. We can check that the device driver is working correctly by running Device Manager, expanding ports, COM and LPT, and selecting the COM port. Next, we need some software to control the laser. LaserGrbl is a good option. It's free and open source. It can be downloaded directly from the LaserGrbl website. To connect to the laser, press the Connect button. The jog key should now be working. The speed can be changed, and also the step size. The 0 point can be set to a new position, and the home button returns the axes to the 0 point that we just set. The laser focus is set with the focus gauge. LaserGrbl can import image files with several different conversion methods. I'm going to vectorize this image. The speed is selected. The G-code command used to turn the laser on can be configured. M3 is typically used for cutting, and M4 for engraving. The engraving size is specified. The Create button generates the G-code. The laser can be switched on at a low value with the Focus button. The axis zeroed. For easy positioning, the Frame button draws around the engraving with the laser. And the Run button is selected to send the G-code to the laser. We can reload the last file. This time I'm going to select Jarvis dithering. LaserGrbl doesn't include any image editing tools, so an external editor is required. A good free open source option is Inkscape, so let's create an image with that. First I'm going to set the document size to the size of the laser bed, 400 by 400mm, and zoom the image to show the page. Next I create a text object. Next I'm going to draw a rectangle around the text. Select the rectangle and the text, then align centre on vertical axis and align centre on horizontal axis. Now I select the text and convert the object to a path, and then save the image as an SVG or scalable vector graphics file. I'm going to engrave the acrylic sample supplied with a laser. The focus is set and the 0 point is set in LaserGrbl. The file is opened. LaserGrbl includes a materials database with values for the speed and maximum power. Selecting Create generates the G-code, and then the G-code is sent to the machine with Run Program. An alternative software package is Lightburn. It costs $60 and it's available as a 30-day trial. Once it's installed, the Ortur laser must be added as a new device. Find My Laser scans for the connected laser, and then it can be added. First, let's make some configuration changes. Settings can be found under the Edit menu, and the units are set to millimeters per minute. A laser fire button can be enabled in Device Settings under the Edit menu. The fire button will only appear after the program restarts. Jog keys can be found in the Move window, and they can be used to move the axes. Pressing Ctrl at the same time gives small steps, and pressing Shift at the same time gives large steps. Power level of the fire button can be configured. Pressing the fire button toggles the laser on and off. Lightburn has a set of drawing tools. Let's use them to create a design. First, the ellipse tool is selected. Unlock the aspect ratio, then the height and width can be entered. Zoom to frame. Select the ellipse and the offset shapes tool. Set the direction to inward with an offset of 5mm. Now we can create some text. Zoom with the mouse wheel or Ctrl plus or minus. Select drag or middle mouse click and drag. Select all three objects. Copy and paste. Create a rectangle and change its height and width. Select all the objects and align horizontal centers. Select the outer shapes and weld shapes to create a single outline. The colour palette at the bottom denotes different layers that can be assigned to different parts of the drawing. Each layer can have different settings. I'm going to use 3 layers, assigning the text to the blue layer, the ellipses to the red layer, and the outer shape to the green layer. The settings for each layer can be found in the Cut Stroke Layers window. The blue layer contains the text which we want to engrave, so I'm going to set the mode to Fill and Line, the speed to 6000mm per minute, and the power to 100%. The line settings are also set to the same. The red layer contains the 2 ellipses which we want to lightly engrave. This time the mode is set to Line with a speed of 10,000mm per minute and 50% power. The green layer contains the outer shape which we want to cut out. The mode is set to Line, the speed to 150mm per minute, the power to 100%, and constant power mode enabled. The order of the cuts is configured under Optimization settings. This is going to be cut from 1.5mm leather. I'm using a baking rack as a laser table and steel brackets to hold the material flat. The focus is set with a focus gauge. We can see where the laser is going to engrave by holding the shift button and clicking frame. And the G code is sent to the machine with start. Images can also be engraved with Lightburn. I'm going to try engraving a ceramic tile using the Norton method. This is where you spray a white tile with flat white paint. I'm using Rust-Oleum all-surface flat white paint, just giving the tiles a light even coat and then leaving them to dry overnight. First I'm going to run a test file to find the best settings for speed and power. Once the engraving is complete, the remaining paint is removed with thinners. The result is a grid of speed versus power, and we're looking for the darkest engraving, which is somewhere around 1000mm per minute and 50% power. The image is imported into Lightburn by selecting File, Import and selecting the image file. The height is changed to 95mm. The speed is set to 1000mm per minute and the power to 50%. The line interval to 0.1mm, the scan angle to 0 degrees and the image mode to Jarvis dithering. Grayscale doesn't work with this method. The frame button is used to check that the tile is in the correct position and the image is sent to the laser with the start button. The white paint is removed with thinners. That's the image burned into the tile. It's very tough and you can't scrape it off. The width of material removed by the laser cutting process is called the kerf width, and it's important to take account of it when parts are made to fit together. There's a kerf setting in Lightburn layers. I'm going to use an online kerf test generator to create a test file. The test file cuts shapes with different kerf settings. The circle and hole with the 0.05mm kerf setting are a very tight fit, and those with larger kerf settings will not fit together at all. So for a friction fit joint, the 0.05mm kerf setting would be appropriate, and for a glue joint, the 0mm kerf setting would be better. With this in mind, I created a design for a French cleat spray can holder in Inkscape, imported the design into Lightburn, and cut it out of 3mm thick basswood with a speed of 150mm per minute at 100% power. The parts were then glued together. Next, I'm going to engrave an anodized aluminium business card using Lightburn's QR code tool to create a QR code image. QR codes can contain web addresses, Wi-Fi and contact information. I've pasted in the web address for the YouTube channel. The QR code is inverted by drawing a rectangle around it. The objects are aligned. And the size and position modified. The speed is set to 100mm per minute with 100% power and constant power mode. Next, I tried engraving a mirror. IKEA is a good source for cheap mirror tiles. To aid alignment, I created a rectangle around the image with a very low power setting. The image speed was set to 600mm per minute with 70% power. The mirror is engraved from the back and any text should be flipped. Afterwards, I cleaned the back with dishwashing soap and a toothbrush. I cut out some basswood frames, glued them together and added an LED strip to make a light box. Then the engraved mirror was added to the front and another mirror to the back. Next, I tried engraving denim jeans. The speed was 10,000mm per minute, 100% power, line interval 0.5mm and crosshatch. Then stainless steel, I coloured this with a Sharpie. The resulting engraving is very tough. Next, 3mm black acrylic. This cuts easily. Then 6mm pine wood. This also cuts well. And 6mm plywood. Laser safe plywood gives the best results. Some plywood is hard to cut. Glass was next. This is a microscope slide and it was coloured in with a whiteboard dry wipe marker. The laser isn't hot enough to melt the glass, but instead it creates a series of small fractures. Different glass gives different results. Then transparent acrylic. Again, I coloured this with a whiteboard marker. Next, slate. Then 2.5mm thick veg tan leather. This would not cut with any settings, it just burned. So I 3D printed an air assist nozzle, connected it to the shop compressor, and then it cut very easily. I also tried cutting 6mm plywood again, this time with the air assist. It didn't change the power or speed settings required, but it did give a cleaner cut. And finally I cut 6mm pine wood with the air assist, and again it didn't change the settings required, but the cut was cleaner. Okay, hopefully that's given you some idea about what you can do with the machine. I've been testing it for several months and it works very well. The laser can directly cut and engrave several types of opaque materials. Metals and transparent materials normally require a coating of paint or ink before they can be engraved. The laser ablation process creates smoke and fumes, so ventilation is essential. LaserGrbl is a good software option, but I'd also recommend trying Lightburn. If you're interested, the link is in the video description. Thanks for watching, and see you again next time.